Hey class, welcome to our last mini lesson on Unit M, Multiple Linear Regression. We're going to take a look at M18 through to page M21. And just a reminder that there's additional problems at the end of Unit M, starting on page M22, and it's got the answers after that. It actually shows the answers or the output in a slightly different form. It's using something called Minitab, and I thought about redoing that using Excel, but I wanted to just show you that there's different ways, different programs that do this. You'll find the stepwise regression output quite interesting on page M24. Now, you're not required to know how to read that output, but I thought it would be interesting to show you what other output looks like, but it's the same numbers if we were to do this by Excel. Anyways, let's get back to this particular lesson here, and we're looking at dummy variables. Now, what dummy variables is about is, you might ask the question about, okay, regression is dealing with interval scale variables. Things like, of course, with our house prices, we're looking at things like house prices, which is interval, and then we're looking at square footage, which is interval in nature, number of rooms, number of bathrooms, number of fireplaces and bedrooms and things like that. And those are all interval scale variables. And that's what regression is really built for. But the question comes up is there any way to insert a nominal variable in there? And the answer is yes. What we do is we create one or more dummy variables. We're going to take a look at an example where you've got a dummy variable with, a nominal variable with just two classifications. So, for instance, it could be something like, are you a student or are you not a student? What's your gender, male or female? Recognizing that some people might put down other, but if you have not enough people who have put down other, just a few people, you may not be able to include them in your analysis, but you would certainly talk about them in the summary of the variable there. But you'd be left then with male, female. And so anything there which has two different categories we will take a look at. And then we will briefly talk about how you would extend that to a nominal variable that has more than two categories. When you've got two categories, so I'm taking a look now on page M18 in the first paragraph here, we're going to be taking a look at this guy right here. This is the natural gas variable, and it takes on values of 0 or 1. Now, if the original variable was the type of gas, and we had natural gas or not, what we generally do, or what we always do, I guess, in dealing with dummy variables here, is you create a new variable named after one of the categories. So in this particular case, we're going to call it NG for natural gas, and then a house that is heated by natural gas would be would have a 1, and then if it's not heated by natural gas, it would have a 0. You do the same thing for gender. So if you've got males and females, you would choose one of those variables. Example, where I got the females. So if we had a variable called female, then anyone who's a female would be denoted with a 1, and anybody who is a male would be denoted with a 0. So that's what you do, is you name the dummy variable according to the category coded with the 1. So again, gender would be called females, and it doesn't matter which one you choose, whether it's male or female, but just make sure that if it's called female, that the females are 1s and the males are 0. When the dummy variable is included in a regression model, it acts as an intercept shifter. So I'm going to show you what I mean by that. And we'll take a look at an example here. And then later, we're going to add something here called a slope shifter. And I want to show you how that works. So we'll get to that on page M20. But let's start with a couple of simple regressions here, first of all. So regression number 7 is listing price on square footage. We've seen this guy before. This was regression number 2. So we've seen this before, right? We had the listing price of the house is equal to minus 1496. I'm going to write this down in a sec. 0.62, and we've got plus 42 times SQF, and we have an R squared value here of 61.1%. So we saw all that in the last couple of units when we were talking about multicollinearity and then how to correct it using stepwise regression. And what we've got down here is that the p-value, of course, for SQF is significant. So square footage is a significant determinant of the listing price of a house. Let's go and draw that graph, a real quick and dirty graph here, along with the regression line. So in question 15 here, this is on page M19, it says, what's the R squared value and what's the equation for the line, and then sketch the regression line. So what we've got here then is the R squared turned out to be 61.1%. So that means that 61% of the variation in listing price is explained by the size, square footage alone. Okay? And then we can come up with the equation for the line, which is list hat is equal to minus 1496.62 plus 42.00 SQF, and that's just from the regression output that we looked at. All right, let's do a quick sketch here on this. And so we're going to have something that looks like this. Looks pretty good. And then I'm going to have a regression line has actually a negative slope. It's kind of, I'm sorry, a negative intercept and a positive slope. So it kind of looks like that. So let me just label a couple of things here. So we've got price is our y variable, and we've got the size in square feet as our x variable. And then what we've got here then is minus 1497 or so, which is our intercept. And then we've got a slope here, which is 42, like that, 42.00. So that's the slope of the regression line. Now again, you might wonder, how can you have a negative intercept here? And the reason is that, remember that regression is good within a certain range. So it might be something like, might be something like this, right? And that, something like this. So this might be something like, I think the smallest house size we had was 1,860 square feet. So you wouldn't want to go much below that. And then it went up to 4,000 square feet. So within that range, of course, you end up with a positive price here, whatever that is. So you could stick 860 into that equation and then figure out what that list price is. I'm not going to do that. I'll assume that you can do the math and figure out what that listing price of the house would end up being. So that's our sketch then of the regression, where you're just looking at the listing price of the house and square footage. All right, now what we're going to do is we're going to add in the dummy variable. So let's go to the output here, back up here, and this is regression number 8. So we're looking at the listing price of the house on square footage and natural gas, which is a dummy variable and takes on values of 0 and 1. So what that looks like then is, let's see, the R squared value actually goes up a bit. So it went from 61.1 to 63.7%. Overall, of course, the two variables together are quite significant according to the ANOVA test, the significance of the F. And then if you take a look down here, you'll see that the p-values for both of these variables, SQF and NG, are significant. So that means that there's a significant difference in listing price of houses between those heated by natural gas and those not heated by natural gas. Now, let's take a look here then at the coefficients here. So we're going to go down here then to number 16 here. It says, consider regression number 8. What is the R squared? The equation of the two regression lines, and sketch the regression lines. All right, so we've got here then that R squared is equal to 63.7%. So a little bit of an increase there by a couple of percent, almost 3%. The equation looks like this. Listing hat is equal to, where's those? So we've got 9433.54 was our intercept, plus 41.20 SQF, minus 11,876.83 times NG. Now, what we can do is we can break this down into two models here. One is where we're talking about houses heated by natural gas and then houses heated by other. Actually, I'm going to do the other first. It's a little easier to handle. So where's my eraser there? Okay. So we're going to have other, and we're going to have natural gas. So this is how the house is heated. So with other, what we've got is listing price of the house is equal to 9433.54 plus 41.20 SQF minus 11,876.83 times 0. So when the house is not heated by natural gas, then the NG variable takes on a value of 0. The dummy variable takes on a value of 0. And what that means then is basically this last term just drops out, and we're left here with this equation right here. Now, let's take a look at what happens with NG. You would have the listing price of the house is equal to 9433.54 plus 41.20 SQF minus 11,876.83 times 1. So remember, the dummy variable takes on values of 0 or 1, and so when the house is heated by natural gas, then it's the coefficient times 1. What we end up with here then is we've got a constant here, the intercept, and then we've got another constant here, which we can add together. And so we can put those together to come up with an equation like this. So 9433.54 plus a negative 11,876 gives you minus 2443.79. Maybe that's 29. Plus 41.20 SQF. So that's what we end up with for our second line here. And you can see why we call a dummy variable an intercept shifter. Both of these equations have the same slope, but they now have different intercepts. So let's go and actually draw that out down here. Let's just get rid of a couple of little things here, like that. And so I'm going to draw a little picture here that looks like this. That looks good. Okay. And so we're going to have here then the price, and we're going to have the size in square feet. We're going to have two parallel lines here. Now look, now I might get these a little off. They're supposed to be parallel. All right. And then another one, which is down here. Those are pretty close to being parallel anyways. This one probably is too high. Can I get that guy? Oh, yeah, okay. Just going to bring them down here. So I've got a lower intercept here. And just going to clean that up a little bit. Yeah, okay, good. So what we've got here then is the higher line is actually for other, right? So that corresponds to this guy up here. And that has an intercept. Oh, I've got the, oh, sorry, no, this is, let me move these guys around a little bit again. Yeah, this was actually 94. Yeah, that looks better, okay. Yeah, that's higher. Okay, so this line here is the other line. And that corresponds to an intercept of about 94.34. And then this is the NG line, and it has an intercept of minus 24.43. And the difference between these lines, the vertical distance, actually is that 11,877, which is the value of the dummy variable. Are they significantly different? Yes, because this guy right here is a low p-value, which means that this is a significant difference between the two lines then. All right? So there's the equations for the two lines. And let me just summarize that last statement and say, because the p-value of NG is less than your alpha, 5%. So it was about 0 or 1%. What was that? Yeah, it was 0.01. So it was 0.01. Then, therefore, there is a significant difference between the two lines. And what we're saying then, the conclusion here is that therefore, for all house sizes, houses heated by natural gas have lower listing prices. Okay, and our best guess then, on average, is they're about $12,000 less in price. So that's how you do that. Now, the problem that we've got with that, though, is that although we can split the two lines into two parallel lines, do they really have the same slope? That's the question. And so we're going to create something now called a slope shifter here. So we're going to take a look at that. Just before we do that, I want to just take a bit of an aside here and talk about, well, how do you actually deal with problems where you have a nominal variable that has more than two categories. So in this particular example, what if we're looking at, say, quarters? Well, what you do in this particular case then is you set one of the quarters, in this case it'll be quarter 1, to be the base case. So quarter 1 is the base case. And then what we do is we create 3 dummy variables like this. So for quarter 2, quarter 3, and quarter 4 from the original quarters variable. And what you'll see then is that if it's quarter 1, it actually takes on values of 0 in all 3 of these other quarters. Otherwise, quarter 2, of course, takes on a value of 1 when it's quarter 2, quarter 3 takes on a value of 1 when it's quarter 3, and quarter 4 takes on a value of 1 when it's quarter 4. So you always have 1 less than the number of categories equals the number of dummy variables. So the only ones that we'll be dealing with in practically in our class here then is going to be 2 classifications. So things like male, female, natural gas or other, natural gas or not natural gas. And so we'll only do that in terms of calculations, but I do want you to know this idea here is if you had 4 quarters, a variable of quarters, then you would have 4 minus 1 is 3 dummy variables, like that. And we won't do any actual regressions with that. Okay, now, that was an aside here. Let's get down to this bottom part here, which is taking a look at this concept here then of the slope shifter. So regression 9 shows the effect of adding a slope shifter to the model. And the slope shifter is constructed by multiplying an interval scale variable, in our case SQF, by the dummy variable, which takes on values of 0 and 1. And the coefficient of the slope shifter is added to the coefficient of the interval scale variable to obtain the slope of the new line for the second category. To show you just a little bit better, let's, what page am I on first of all? M20, okay, M20. So I'm just going to go back to the early part of M here, where we had the actual data right here. And I'll go back even a little bit further here, where we first introduced the problem. And now we're taking a look at these guys down here. Oops. So we're talking about NG, which is the dummy variable, takes on values of 0, 1. And then if we multiply the NG times SQF, then you'd end up with a slope shifter. What that looks like is over here. I briefly talked about this in the very first lesson that we had for Unit M. But here's NG, which takes on values of 0 and 1. And then when you multiply the SQF, when you multiply here the SQF value, 1340, times NG, this is a house with natural gas, then you end up with the slope shifter, NG times SQF, of 1340. So for these first 3, where you've got the NG equal to 1, they're just duplications of these guys here. But then when you get down to the 4th one, it would be 2000 times 0, and so it blanks out. So when you're dealing with non-natural gas heated houses, then the slope shifter simply becomes 0. So the NG SQF is a replication of the SQF column for natural gas houses, and then is zeroed out for other houses. So let's take a look then at how that works when we're back down here, and we're looking at right in here. Okay, so regression number 9 here then is taking a look at the listing price of a house on SQF with the dummy variable, and now also with the slope shifter here. And we end up with this down here. Now, watch what happens to the R-squared value. R-squared value goes way up, 74.8%, from the original 61% when it was just SQF. Okay? And all of these coefficients here then, for SQF, for the dummy variable, and for the slope shifter are all significant. All right, so high T-star values here. And of course, no surprise here that the overall ANOVA shows that these three variables together significantly explain the listing price of the house. All right, let's draw that out and see how that looks there. So, consider regression number 9. What's the R-squared value? And so on. I'm going to actually try to keep everything over in the left-hand side so I can keep the right for writing out the equations. So we've got the R-squared significantly jumps up. It goes to, what was that, 74.8%. So originally it was 61.1%, and then we added the dummy, and it went to 63.7%. And now, by allowing the two lines to have different slopes, they jump up to 74.8%. Here's the equation, just looking at the coefficients column from regression number 9. And we've got here minus 49,831.46. And you know what, that's good. And then plus 72.34 SQF plus 65,769.78 times NG, and then minus 41.45 times the slope shifter NG times SQF, like that. Now we can come up with two lines here. So let's come up here with, we'll start with an other line, because it's a little easier to handle, and then we'll come up with an NG line. So if you heated by something other than natural gas, you would have the listing price of the house is equal to minus 49,831.4 plus 72.34 times SQF plus 65,769.78 times 0, right? When NG takes on a value of 0, when it's other, minus 41.45 also times 0. Remember we said that those values blank out because it's NG times SQF. So what we're left with then is just these first two terms, which is the line for other. Then what we've got is, for NG, we'll have listing price of the house is equal to minus 49,831.46 plus 72.34 SQF plus 65, looks like I'm missing a number there, 769. This is 7, here, I'm just going to clean that up just a little bit here. Sometimes the pen just doesn't catch it when you're writing on glass. 65, 769.78. So down here, 69.78 times 1. And then minus 41.45 times what? Well, not 1, but SQF. So remember that that slope shifter variable takes on values of either 0 or SQF, depending on what the dummy variable is. What we can do now is we can collect terms. So we can say, well, here is a couple of constants right there, and there, which we can add together. So we're going to add those constants together. And then we've got these guys here, which are the coefficients. Let me use a different color. No, I'm going to use black here. Okay. And then we've got these guys here, which are the slopes of SQF. And they can be added together. So what we end up with then is something that looks like this. The listing price of the house is equal to minus 49,831 plus 65,769 gives us 15,000. 938.31 plus, and now we're going to add the two slope coefficients for SQF, so 72.34 minus 41.45, and that'll give us plus 30.89 SQF. So there's the equation now for NG. So let's draw that out now. I'll do that over here. Okay. Like that. All right, so we're going to have here then price, size, square feet, kind of thing there. And we're going to have a line that looks like this. This will be minus 49 thousandths. And then it has a fairly steep slope here for the other. So how about like that? And then we're going to have another one, which is going to be an intercept of about 15,000, 16,000, and a lesser slope, like that. So this is this second one that I drew here. That's your NG line, natural gas. And then this is your other. All right, and so what you've got here then is, for the NG line, we had an intercept here of 15,938. I won't put in the decimal places here. And then down here, we had minus 49,831. Okay. And then we've got slopes here. This is a flatter slope of 30.89 for NG. And then this is 72.34 for other. And what we have here is that the difference in the intercepts, which is in the NG variable here, is significant. So there's a significant difference in the intercepts. All right? And there's also a significant difference in the slopes right there. And square footage is still significant. The only other question I want to ask you then is, well, where do they cross? They would cross at this particular point right here, and that would give us a particular X value. How do you figure that out? Well, what you've got here is you've got two equations, and you could set list price equal to each other, and you would end up then with where they equate. The other thing that you could do is you could just simply notice that you could subtract this one from this one up here at the top, and you'd end up with this left over. And if you set that part equal to 0, so if I'm subtracting this guy here, the other, from the main equation, then what happens is the first two terms drop out, and then you set this equal to 0. So you bring the constant over to the other side, so to be minus 65,769.78 is equal to minus 41.45. This would be this part down here, right? And then you could just solve for SQF. And what you would get then is the SQF is equal to minus the coefficient of the dummy variable, in this case, NG, divided by the coefficient of the slope shifter. Okay, this is where they intercept. So that's going to be minus 65,769.28 over minus 41.45. And what you'll come up with here is 1,586. Now again, you can just simply equate the two lines, right? The two regression lines, the equations, and set the listing price equals and gather terms, and that's all you'll end up with, is exactly what was left over, which are the coefficients of NG and NG times SQF. So this is 1586, and so what we can conclude here then is we would say that for smaller houses, and that's for square footage less than 1,586 square feet, then houses heated by natural gas list for a higher price than those heated by other methods. Above 1586, it's reversed. Right? So the other house prices then list for higher. And then you could go on further and explain that by saying that, I think I'm just going to talk you through this part here and say, remember that regression is good within a certain range, like that, right, and that. And so again, we had 860 square feet and we had 4,000 square feet. What I always do is just go in here and say, okay, the smallest house prices that I had in there was 860 square feet. So stick 860 into each of these equations up here for the listing price of the house. Right up here. So put in 860 right there, 860, and then put in 860 here for this guy, and figure out what your listing price is. And I haven't done that calculation, but you can easily do that. And then you can say, and then for houses heated by natural gas, the price then increases by $30.89 per square foot. And for houses heated by other means, the price will increase by $72.34. And those, of course, are the slopes of the regression lines. Okay, last little bit that we want to take a look at is it says, well, how do you know which is the best model when you're taking a look at regression 7, 8, and 9? To determine which is the best model, follow these steps down here. So you start with the largest model, and that's the one containing the dummy variables and the slope shifters. Check the significance of the slope shifter. If it is significant, then you stop there. It's the best model. A general principle in regression is that a model should contain a slope shifter only if it also includes the two variables that created it, even if one or both of the other ones are insignificant. And that's probably due to multicollinearity. Remember that there's a great deal of correlation, great positive correlation between square footage and the slope shifter, which is ng times SQF, right? So SQF and the ng SQF values take on exactly the same values, except where ng is equal to 0. So you would expect actually there to be a high correlation between them. And if we went back up to the correlation matrix, in fact, let me take us there if I can. There we go. Let's go right back up to the beginning here and take a look at the correlation matrix. I think that was about page M10, was it? Let me just find that. It's kind of hard to read those small guys there. Page M12. So that was next page here. Okay, here's the correlation matrix. Now remember when we first looked at this, we didn't look at the NG and the SQF lines, but take a look at what we've got here. We've got a very high correlation here between NG and SQF, and NG and NG SQF, very high correlation, which is what we would expect a dummy variable with the slope shifter. And with square footage, it's still pretty high here with NG-SQF. Not quite as high here then. It's not very high at all, actually, with the dummy variable itself, but it's actually quite high, 0.398 with SQ and NG-SQF. But this guy in particular is very high. So when you put all those variables together, you should expect a multicollinearity problem. And so it's quite possible then that one or more of these three variables would end up being insignificant when you put them all together. Now, in our particular case, they're quite strong variables, and so they actually all end up being p-values which are really low, and so we're fine. But the way that you start is just by looking at this guy, the p-value for the slope shifter. And if it's significant, you stop there. Oops, additional problems. Okay, so check the significance. If it's significant, then this is the best model. Even if one or both of the other variables are insignificant, and that's because of multicollinearity. All right, but we would still say that that is the best model. If the slope significant is insignificant, then eliminate it and take a look at the model with the interval scale variable, so square footage and dummy, and eliminate the dummy variable if it's insignificant. So you just kind of work up backwards, kind of like what we did in the stepwise regression in a sense. And so that's what we've got there. So which of the three models is best at explaining the effect of house price and listing price? Regression number 9, which includes the slope shifter. And of course, if it includes the slope shifter, it also includes the dummy variable. It had an R squared, which was a big jump up. It went up to 74%, I think it was. Let me get back to my page. 74.8%, which was a big increase. And the slope shifter, so this is a big increase, big jump. And most importantly, the slope shifter is significant. All right, so that is it when we're talking about dummy variables. That brings us to the end of the unit. We've got some additional problems starting on page 200, M22. But that is the end of this mini lesson. That's the end, actually, of Unit M, and that's the end of all of our lectures. And so thank you very much for joining with me on this. Have a great day.